In this lecture, I'm going to say a little bit more about the van der Pol oscillator, and in particular, I'm going to introduce the Hopf bifurcation. The van der Pol oscillator is, now there's a couple of different variations of it, but this is the form that I'm going to use. That's what it looks like as a two-dimensional system. You can also think of it as a single variable second order dynamical system. The part here is simply the standard harmonic oscillator. This part is damping, and you can see that the damping is nonlinear, so that's kind of what makes this more interesting than just a harmonic oscillator. In fact, if x is small, then this term will be positive, and that term will have the opposite sign to mu, which means that if, for example, mu is positive as well, then for small values of x, the damping is effectively negative, which is sort of the opposite of damping, and oscillations will tend to grow. But then if x becomes large enough, this term will become negative, and the overall term here will be positive, and that corresponds to regular damping, which reduces the amplitude of oscillations. So what that means is that for mu greater than 0, the picture is roughly that things are coming in from far away and they're going out from the origin. And so we would expect to find some kind of stable oscillation right there in the middle. However, if we reverse mu, then the effects are also reversed, and for small values of x, the damping term comes out positive, which gives damping, and for large values of x, the damping term comes out negative, which gives this sort of anti-damping, which is hard to draw. Which suggests that there is probably something like an unstable limit cycle happening here that separates trajectories that spiral inward from those that flow away. Okay. So first, a little bit of linear stability analysis. It should be clear that for fixed points, y must be 0, and once y is 0, that zeroes out everything over here, and we're left with x equals 0. So there's only the one fixed point at the origin. Again, if you zero out mu, then you're just left with the harmonic oscillator. All orbits are circles, and the origin is a center. For other values of mu, we can do some linear stability analysis. This is the Jacobian matrix in general. We're generally going to be interested in its value at the origin. And if you look here, I've picked out the trace, which is the sum of the two diagonal elements, the determinant computed in the usual way, and then the discriminant here is the b squared minus 4ac from solving the characteristic polynomial. So here's one way of looking at this. If you remember, there's this diagram that separates into saddles, stable nodes, stable spirals, and unstable spirals based on the determinant delta and the trace tau. Since the determinant is fixed at 1 and the trace is mu, the trace can vary, but the determinant is going to always be the same. So that means that the fixed point will always have a linearization somewhere along this line. If you imagine for large magnitude negative numbers, that puts us down here because the discriminant will be positive either way. I'm drawing this the wrong way. The discriminant will be positive for mu of large magnitude. It will then become smaller as mu decreases, the discriminant will get all the way down to -4 when mu is 0. But then it isn't going to change again. So I've actually drawn this maybe a little bit too far. So the discriminant will become negative. The trace, yeah, so sorry, the trace will, yeah, the trace does go all the way through. The discriminant is positive whenever mu is large enough. Okay, that's what I wanted to get to. So if you imagine now mu starting out down here is a large magnitude negative number and flowing upward, what kinds of changes to the vector field are we going to see? Well, we're going to see the origin start as a stable node, develop into a stable spiral, switch stabilities actually. It'll become a center right there. That's at mu equals 0. So let me do this. And then it'll become an unstable spiral, and then eventually become an unstable node. That means that there are going to be some interesting changes to the vector field overall. Close to the origin, but not entirely at the origin. So let me show you some calculations. Okay, come on, change scenes. There we go. So the gray arrows in the background are a stream plot. So that's the vector field. And then the two crosshairs are starting points for two different trajectories. Let me pop open this, and you can see this is for mu equals -3. For this value of mu, the vector field has a stable node at the origin, and that's what you see here. If you go in reverse time, this solution backs up and seems to be coming from a sort of lopsided closed orbit. Same thing, if I start outside here, the solution seems to run off to infinity in forward time, but if you back up to see its history, it seems to have come from the same closed orbit here. So what we are seeing, I'm going to sort of sketch over here. There's the other window. So for mu much, much less than 0, we have a stable node at the origin, and there is some kind of unstable limit cycle out here. Yeah, maybe I should just leave this. Something like that. Okay, so for mu a little bit less than 0, we should be able to capture this behavior. So that's a stable spiral. Oops. No, I need that. So for that, I'm going to move mu up to -1. Now you can see the stable spiral. There's still this unstable limit cycle that's lurking here. Part of why this has to be here again is to separate trajectories that spiral into the origin from trajectories that flow away to infinity. Okay. So for mu less than 0, but not a whole lot less than 0, now there's a stable spiral at the origin, and there's still an unstable limit cycle on the outside. Let me go back to here. If mu equals 0, then we should be able to see a center, because the dynamics reduce actually to the linear system that is just the harmonic oscillator. So let me set mu up to be 0. And sure enough, there you can see that the solutions are all perfect circles. The origin is neither stable nor unstable in this sense. Well, it's stable but not asymptotically stable. Let me be perfectly correct about it. I haven't made much of that distinction in this class, but that's something we can get into if you are interested. So there we have a whole nested family of closed orbits. So that's mu equals 0. Now here's where things start to get interesting. If we increase mu a little bit more, we should get to a place where the origin is an unstable spiral. So let's see, what do we know when mu equals, say, I found that 0.05 gave some interesting results. We know that the origin has become an unstable spiral. Let's take a look at that in a little more detail. Okay, so here you can see at mu equal to 0.05, the origin has become an unstable spiral. It may be a little bit difficult to tell which way these orbits are moving, but this is the past on the inside, and then that's the future on the outside. And we know that because of the linear stability analysis. So same thing here is a trajectory that starts way out here somewhere. And you can tell from here, the past is way up here, and then the future is starting to spiral in. If I grab my my initial condition and move it out here a little bit, you can actually see that here it's very close to that stable limit cycle. If I move this initial condition, you can also see now I'm getting closer and closer to that stable limit cycle. So what's happened is that this stable limit cycle has essentially popped out of the transition from a stable spiral through a center to an unstable spiral. This is something called a Hopf bifurcation. Okay, so let me give you kind of a cartoon of what's happened again. We started with a stable spiral. Then we went through a point where we had a linearization that gave us a center. So that means that the eigenvalues are purely imaginary. Now, as to what the vector field actually does in this case is very case dependent. Every nonlinear system does something different right there. But then once it changes stability, there's still this sort of general inflow from the larger scale vector field, which means that a spiral can't just swap stabilities. Instead, it has to basically shed a limit cycle. And in this picture, the limit cycle will be stable. So here you have an unstable spiral surrounded by a stable limit cycle. This is the supercritical case of a Hopf bifurcation. And the distinction there is that the limit cycle in question is stable. Another way to think about this is suppose that you have a stable limit cycle with an unstable spiral on the inside. You can imagine it shrinking until it finally vanishes, leaving a stable spiral where there used to be a limit cycle and a fixed point. Let me fill in a little more of this vector field to maybe make the picture clearer. The size of the limit cycle actually it has sort of a predictable size. I'm not going to get into that, but it doesn't appear at some unfathomable distance from the fixed point. It appears initially right on top of it and then slowly grows as the bifurcation parameter increases. And so on bifurcation diagrams, very often what you will see is that, actually let me draw the background in gray. So here's mu, and say I'll draw x. Really this should be a plane. Yeah, I can draw it like that. Well, if I'm going to do that, I may as well put x here and y there. So initially we had a stable fixed point at the origin, and then we had the stable fixed point change to being an unstable spiral, and around it is an oscillation, stable oscillation. So you will sometimes see bifurcation diagrams drawn in 3D like this, or you may just see that much of, that much of it. So it sort of looks like a pitchfork bifurcation, but the idea here is that this is a limit cycle. There is also something called a subcritical Hopf bifurcation. So let me come over here and draw that for you. In a subcritical Hopf bifurcation, you have actually an unstable limit cycle surrounding a stable spiral. And you start from there. As you change a parameter, the limit cycle shrinks until it finally hits the origin, well, hits the fixed point and vanishes, leaving an unstable spiral with no limit cycle at all. So that's a subcritical Hopf bifurcation. It can also run the other direction. That just depends on basically the sign of the parameter that you're working with. So what's sort of important about this is that if you're counting on behavior like this for some reason, it's really unfortunate when the stable behavior disappears. So this is something that sometimes causes physical devices to fail. You change a parameter and all of a sudden, instead of having a nice stable fixed point somewhere that you oscillate around, you suddenly have an unstable fixed point, and it can lead to catastrophic results. This does not seem to be present in this version of the Van der Pol oscillator, unless you were to reverse time then the subcritical would the supercritical would be turned into a subcritical. So okay, so there you go. That's the van der Pol oscillator. One last picture. Let me show you what happens if we increase mu further. So there is the stable limit cycle. It's gotten kind of lopsided. And if I keep going forward here, eventually that fixed point in the center switches from being a spiral to being a node, but it's still surrounded by a stable limit cycle. So that can happen as well. That's well away from the actual Hopf bifurcation point, which is at mu equals 0. Okay, so there you go. Van der Pol oscillator and a quick introduction to Hopf bifurcations.